Let's take a look so we can stay on schedule. My name is Bartsch. I'm the CEO and co-founder of a company called Aero. We work on electric power systems for a wide array of aircraft in different markets. And a lot of what we do right now is on hybrid electric aviation. So I'm here today to talk a little bit about hybridization of electric aircraft, which is a relatively new field in aerospace propulsion. So I have to share some background with you on that and some of the progress the industry is making and give you a glimpse of what's coming. So just to get started here, I've been in electric aviation now for about 10 years, and actually that's a picture of one of my business partners and co-founder of Aero, and that's the two of us in front of a battery electric ultralight at the time when I was working with back in 2013. And so I was fortunate enough to be around in the early days of electric flight. I got to log some flight time in some of our test aircraft once the test pilots were comfortable handing them off to the rest of us. And got to experience a lot of the benefits of electric flight. But I also got to experience firsthand a lot of the drawbacks of electric flight with the current technologies we've got. And so that led over time to several of us getting together, forming Aero, and getting into hybrid electric power systems as a big part of what we do and as a way of jump-starting the electrification of flight. And so that's a picture of some of our team over there with what we call one of our iron birds. That is not flight-ready hardware, that's research hardware. We've got some newer things you'll see a little later in the presentation, but that is our very first full-scale power plant unit that we're running on the ground. We've been running that now for about a year and a half. So with my experience in battery electric aircraft, I've been flying it since 2013, been involved with them earlier than that, hybrid electric power plants since 2017, and I've now worked with about 50 different companies as people we've built relationships with who are developing aircraft in this space. And so what I'm really here to do today is to give you some contrasts between batteries and hybrids and talk a little bit about how electrification is playing out and where both of these technologies fit in. So right off the bat to start with, we have to ask ourselves, why would we want to electrify an aircraft? So how many people in this audience have driven a hybrid electric car? Quite a few. How many of them have driven a battery electric car? All right, fewer, but still quite a few. How many have flown an electric plane of any sort? All right, when I asked that question a few years ago, I was the only one raising my hand. I'm glad to see that there's starting to be a few of us out there. So this is a really important question because we need to actually think a lot about what are we trying to achieve when we electrify aircraft. So when we look at aerospace, efficiency, emissions, and noise are the biggest challenge that the overall aerospace industry faces globally. And a lot of the motivation for electrification is to be able to, in part or in full, address some combination of those three concerns. So that's really why we're here, and that's what's motivating the industry. And propulsion has historically enabled aircraft design. So when you have a revolution in power plants, it changes what aircraft look like. And so if we go back to the early days of the jet engine, 1940s and 50s, and even a little bit of the 60s, as that was playing out, the very first thing that people did with jet engines is they put them on airplanes that looked a lot like a piston engine airframe. And so that P-59 up there in the upper corner, that was one of the early jets. That was an important stepping stone. It wasn't a particularly compelling aircraft because it was primarily a piston engine airframe with a turbine engine power plant and it wasn't really matching built. However, it was amazing how quickly we got from that E-59 to that F-104. That F-104 is a plane that would be inconceivable with piston power. You can't go Mach 2, you can't have wings that small, you can't have that high wing loading, all kinds of things. But that airplane was designed around a turbine engine. Likewise, with the electric motor, the first things that a lot of us did, myself myself included, was build aircraft that looked kind of like a conventional aircraft. That's a VD-430, that's one of the aircraft I was involved with early on. Great aircraft, flies a lot like a rotor glider. But once again, the big idea is not how do you take existing airframes and put electric power into them. It's how do you take electric power and design things you could never do before, like all of those things on the lower order and many more. So really, propulsion enables aircraft design. And one of the big things that's going on in electrification is using arrays of electric motors, what we call distributed electric propulsion, where you don't have one power plant or two power plants. You might have 10 or 14 or 18 or more. And you can do that weight efficiently and reliably with electric motors, whereas you would never want to think of putting 15 piston engines on an aircraft or 15 turbine engines on an aircraft. It just wouldn't make sense. And one of the things you get when you have a whole lot of sources of thrust around the aircraft is you get the ability to blur the lines between propulsion, between attitude control, and between active aerodynamics. So the benefits that we're really going after with electrification are primarily to design new types of aircraft that can benefit from the rules of designing electric aircraft. And those rules are different than designing a turbine-powered aircraft or a piston aircraft. You can have a lot of propulsion units, and doing things with a lot of propulsion units is very exciting for the reasons behind all these programs, and many more, including a couple that we saw fly here yesterday. However, there's a dark side to electrification, and that has to do with batteries. And I've been fighting this myself for 10 years now. I love electric aircraft, love flying battery electric aircraft when I can, but there's a big, big difference between what gets promised and what you can really get when it comes to batteries. This is a chart that I've kept over the last 10 years, where all the red dots up at the top are the various things that I've been promised over the years, either directly or in press releases or whatever. And this is in watt hours per kilogram. That's how we measure how much energy there is for a given amount of weight in the battery. The higher is better. So people have been promising me things all over the place and continue to do so. That green line at the bottom is what I can actually get. That's very different than the red dots at the top. And so we'll get to questions a little bit later on here, so I will have a set of questions we can come back to. So that bottom line there, we're currently at cell level, we're able to get high 200 watt hours per kilogram. Pack level, we're able to get just over 200 watt hours per kilogram for aerospace pack, which is great, but it's a long ways off of what we all want. So the other side of that is if we then take what we can actually get, a pound of fuel delivers about 20 times the propulsive energy of a pound of the best lithium batteries that I can get on the market. And so that 20x differential is huge. I mean, if we told you you could get an engine that was 20 times lighter, or if we told you you could get anything 20 times lighter for an airplane, you'd go for it. The fact is, fuel is 20 times lighter than batteries right now. And there are some things we can do with batteries right now. Some things already flying, that's exciting. There are also a lot of things we can't do, and unfortunately aren't going to be able to do for quite a while on the trend of the rock. And just to bring that home about what does a 20 times weight difference mean? I just ran some rough numbers here, and this is all ballpark engineering, so take this with a grain of salt, but it's directionally correct. You take a conventional Cessna 172, it's got 53 gallons of fuel on board, and the engine on the front weighs about 300 pounds. The good news is if we wanted to electrify that, leave the payload and everything the same, the electric motor and the inverter are actually lighter than that gasoline engine, so we get a little bit of the weight back. So if we take all the fuel weight that's available and we take the benefits of going from a piston engine to an electric motor and save a little bit of weight there, we have about 500 pounds available for the battery. The best I can do with a 500-pound battery right now is the equivalent of 4.6 gallons of avgas. So that's the big challenge. And when you think about electrification, you got to think about the Cessna 172 with 4.6 gallons on board. How useful is that? What can we do with that? And if you're designing a motor glider that's extremely efficient, you can actually do something with 4.6 gallons. If it's a draggier, heavier plane with a bigger payload, like a 172, you've got a fuel emergency before the wheels leave the runway. You actually don't have your VFR minimums on board the moment you take off on the ground. So for a lot of the things that all of us in the electric community want to do with airplanes, if we want to electrify, we need more energy on board. Electric motors are great, batteries are part of the solution, but it's not the whole solution. So the good side is we can make new types of aircraft, we can merge propulsion, attitude control, active aerodynamics. The bad side is 20 times energy deficit and the hypothetical 4.6 gallon 172. So that brings us to hyperelectric aircraft, which is the topic of today's talk. So what is a hyperelectric aircraft? And the answer to that is it's kind of similar to a hybrid car. It's also kind of different than a hybrid car. So a hyperelectric aircraft, you can think about that as a bridge between conventional propulsion and battery electric power. And what you've got on that aircraft is a combination of systems that you find in conventional aircraft combined with systems you find on an electric aircraft. So you've got a combustion engine on board, you've got liquid fuel on board, but you've also got batteries, electric motors, and the control hardware and software for those on board. So that you can get some of the benefits of electrification, you can also get some of the endurance of liquid fuels. So there are two types of hybrid architectures that people will talk about. And actually, if you walk around the show here, you will even see both series and parallel hybrids being worked on by some of the innovators here at Oshkosh, including Vertigo, but not limited to us. A series hybrid, much as the name implies, everything is in series. So you've got an engine that's spinning a generator. It makes electrons flow down a wire. And then you've probably got a battery attached to that wire somewhere, so you can flow power in and out of that battery. And then far into that wire, there's a motor that spins a prop. And so you can spin that prop with power coming from the engine or from the battery, but that electric motor is always what spins the prop in a series hybrid. The engine has no mechanical connection to that motor. It's purely pumping electrons into the system that are consumed on the other end. This is primarily useful for those distributed electric propulsion scenarios where you may want to have one engine, you may want to have 10 propellers. This is a much better way of doing that than having drive shafts, gearboxes, and a whole bunch of mechanical complexity. There were a whole lot of things tried in the 1950s and 60s, particularly with mutual aircraft, that were really interesting new designs for the aircraft. The aerodynamics worked, the controls worked, the mechanical distribution of power was the Achilles heel. Everyone had to use gearboxes, drive shafts, a lot of weight, a lot of reliability issues. Using a series hybrid is a much easier way of moving power all over that aircraft and using it for any need. A parallel hybrid, unsurprisingly, you've got power sources in parallel. So you've got an engine, however, that drive shaft reaches all the way to a propeller. Maybe not all the propellers on the aircraft, but at least one of them can spin directly off the engine. And then you've got some clutches engaged, and then you've also got a motor and generator. It's a combined motor generator as well as a battery. What that allows you to do is you can run the prop directly off the engine, you can run it directly off the battery driving that motor, or you can run the engine and overdrive the prop such that you've got extra power and you pull that off and that motor becomes a generator and now you're putting energy into the battery pack. This is a lot more like what a car does. This is a lot more like what a diesel locomotive does. So there are analogies that we're all familiar with, but these are two different types of hybrid architectures. So is a hybrid aircraft, a hybrid power plant, always more efficient than conventional power? And the answer to that in an airplane is not always. You have to be really careful about what you do with a hybrid that has to do with conversion losses. So I'm going to a series hybrid here now. Every time we convert energy from one form to another, or power from one form to another, there are losses. Most of those losses are in heat. And so a state-of-the-art conversion might give us 96% useful power in those 3 G's phases. About 4% of that leaves as heat or other types of losses. So if we have this series hybrid here that's drawn on the screen, you get 96% up front, and then you get 96% when you convert it back. You multiply those together, and it's about 92% efficient. So that means that in this scenario, just connecting the engine directly to the prop would be 8% more efficient than the hybrid, and you wouldn't have the weight of all that stuff in it. So literally doing that in an aircraft is probably not a good idea. It's one of those things, you can do it, you can fly it. It's not a particularly great idea though to do something like that. However, I talked earlier on about one of the reasons we electrify aircraft is so we can merge together active aerodynamics, attitude control, and propulsion. If you have a whole bunch of electric motors, and for example, you're blowing airflow over the entire span of the wing, you're using it for other things, you're doing active aerodynamics on the aircraft, they can dramatically improve the efficiency of the whole aircraft. Well, all of a sudden, I've got that 92% losses inside the powertrain. But if I've got an aircraft that then is aerodynamically 30% more efficient, I multiply those 2 together, and the net is up 20% up. And so the thing that I wanted to communicate here is it really matters what you do with the hybrid electric powertrain. They can give you big benefits, but you got to consider the aircraft and the power plant. They got to be matched together to get the benefits. So just to answer, what is an electric aircraft? What is a hybrid electric aircraft? It's an aircraft that has a powertrain that has some of our conventional powertrain components, some Hyperelectric components on board, and you're usually implementing these to get better mission capability, longer endurance, faster time to market, and compliance with safe energy reserves. You know, we have to have a lot of extra energy on board an aircraft so that when we fly to our destination and there's weather, the runway is blocked, or whatever, we got to be able to plan safe flights. So it's not just about getting from point A to point B, it's getting from point A to point B with the reserves on it. That's often a big challenge. So what does a hybrid power plant look like? Well, this is kind of a flow chart here that has a whole bunch of stuff on it. But basically, that hybrid power plant has an engine, it's got a generator, a bunch of power electronics, cooling systems, control systems, and a battery pack where you're storing some of the energy sometimes. And I will say, one of the things that gets forgotten a lot is cooling. We spend a lot of our effort, here we go, on cooling all of these systems because you've got an engine that likes to get hot, a generator that likes to get hot, power electronics that like to get hot, and all of these things get hot at different rates and different temperatures. And so efficiently cooling these things is actually one of the keys to making hybrid systems that are reliable and implementable in a lot of different aircraft. So what you're seeing here, this is actually the first time anyone outside the company has seen pictures of this system here. This is a development system. We've got several of these running now. This is a generation beyond our line curve we saw earlier in the presentation. This is a 150 kilowatt aerial jet set for a test aircraft. I can't tell you anything about the application other than to say it's really interesting. It's going to be going into the air with one of our customers later this year. But that is engine, generator, power electronics, a whole bunch of other stuff built together in a unit that is able to be put on board a test aircraft. And then the next stage beyond this is the hybrid power plant that we're currently developing right now, which has about a third of the physical volume of what you just saw on the previous page, and it's about half the weight. So as we move forward, these hybrid power plants are getting more integrated together, they're getting lighter, they're getting more powerful. So how do hybrid airplanes compare to hybrid cars? And there are a lot of people in the audience here, myself included, who've driven a hybrid car. bunch of energy and heat. How many people in this audience have hit the brakes on their airplane while cruising through the sky? I guess I've actually used speed brakes, technically, aerodynamic brakes, but generally, we don't have brakes that we use very commonly on aircraft. So there's a fundamental difference on why we do hybrid airplanes versus why we do hybrid cars. That hybrid car, it's all about getting the wasted heat that's lost when you hit the brakes. And instead, you regenerate that power, put back in batteries, and you use that energy to accelerate the car again. And that's most beneficial during stop and go traffic, which is great, really impressive for cars. We don't fly airplanes in stop and go traffic. So we got to think about, why do we want to do hybrids in aerospace? Well, it comes back to what I was talking about earlier. We want to enable those new types of aircraft. We want distributed electric propulsion, we want active aerodynamics, and the hybrid is a means to an end. So in the hybrid car, the powertrain itself is inherently more efficient. In the hybrid airplane, the powertrain itself has some inefficiencies and added components that we're adding in. And it's really at the aircraft level that we then get that back as well some and wind up with a net benefit. So hybrid airplanes, it's really all about airplane plus power plant. Hybrid cars is really more just about powertrain. So some other differences between the automotive and the aerospace world. So in aerospace, unsurprisingly, we need a lot more performance out of our components than the automotive industry does. It's just a different market. You know, when it comes to batteries, we're basically there with the latest Teslas. The energy density of a battery inside a Tesla is good enough that that car's got hundreds of miles of range. It can accelerate faster than the supercar. They're reliable, they work. We need about 4 to 8 times that energy density before similar applications in the sky become useful. But it's not just about the weight or the energy density of the battery, it's also about the cycle lifetime of the battery. In a car, if you start using that battery pack and it wears down over time, you know, how many people out there have one of these? Fine. Not everyone's got one of these. 2 years after you buy this, is the battery going to be as good as it was on day one? No. You know, batteries start degrading over time. And in a car, if you lose 20% of your acceleration over a 5-year period, it doesn't really happen. The car still works just fine. In an airplane, if you lose 20% of your climb power, or 20% of your climb rate, that's a big problem. You have to have a power plant that works as well on the final day as in the airplane as it does on the first day of the airplane. And so having batteries that don't behave like what's in this, or derating a battery so that you can count on its performance, that's a big deal. Charge rate's also a big deal, and safety. You know, we can't pull to the side of the road. You know, in a Tesla, if something goes wrong, you can shut the battery off. I was talking to some people who work on automotive high-performance batteries for race cars, and we were talking about the philosophy of designing the control systems around that battery. And they were saying, well, you know, to save the battery, if we see any kind of fault in software, we just shut that battery down, the car rolls to a stop. I said, okay, that's great. How about an airplane? They said, well, we still want to just shut these batteries down. If there's any kind of fault, we're just going to shut the battery off. Protect the battery. I asked them, well, okay, if this is installed in an unmanned drone that's hovering and it's 500 feet off the ground, if you cut the power, you save the battery for a couple of seconds until it hits the ground and becomes a fireball. It really didn't save the battery at all. You know, the battery just has to run, and it has to run even if things are going wrong. And that's just a complete difference in the automotive design process and the aerospace design process. So you add all those things together, and people in my industry, we want to think of ourselves as, you know, we're getting to the point where we're seeing the Teslas of the sky. And particularly in the investment community, everyone wants to buy into the Teslas of the sky. The reality is, though, we're not in 2021 in the aerospace industry. We're in about 1995. So when you think of analogies between aerospace and automotive, the aerospace industry right quite a few. People at Toyota and Honda were working on the Insight Caprice, the Hyperelectric cars. The EV1 was a really interesting technical milestone, but they cost about $300,000 a piece to make. They had very short range. They didn't really meet the market needs. However, the hybrid cars went on to sell more than $200 billion worth of cars over the next 20 years, more than 10 million cars delivered by 2017 just by Toyota. And it wasn't until almost 20 years later that the volumes of Tesla's Model S and then later the Model 3 really started to take off. And so there's just this lag, and we're right here at the beginning of this roadmap. We're not at the end of it. So again, if we want to do things now, we've got to sidestep batteries and figure out how do we get there faster. So what happens if we retrofit an existing aircraft? I've had a lot of people over the years ask me, hey, can we put one of your systems in an aircraft and retrofit it? And sometimes the answer is, that's a good idea. But you gotta be real careful because a lot of the times you're doing that. And turbofan engines are great. Arguably, in a lot of settings, turbofan engines are better than piston engines. So if a turbofan engine is better than a piston engine, that must be a really good idea. Well, the fact is, it's not a really good idea. I wouldn't turn down the opportunity to fly that, but I would never buy that or fund that. And the reason is, an airplane is designed around a specific power plant. The speed the airplane goes, the payload, the weight fractions of the aircraft, the center of gravity that the components are supposed to be at, the volumes of the aircraft, fuel tank size, all of these things are really designed around having a certain power plant in the aircraft. And if you put a turbofan on a 172, you can undoubtedly make it fly. We would all watch it during the air show every afternoon here at AirVenture because it would be really cool, and you would sell absolutely none of them because it wouldn't be a marketable aircraft. And so that's the thing you've got to think about in retrofits, is there are a select few cases where the parameters in the old aircraft and the parameters in the new hybrid aircraft actually match up. Generally speaking, though, it comes back to what I was talking about earlier. To get the benefits of electrification and hybridization, the airplane needs to be designed around it, just as the 172 isn't designed around the turbofan that the Citation is. So what roles do the battery and the fuel play in a hybrid aircraft? You've got two sources of energy, two sources of power. We talk a lot in electrification and hybridization about peaks and valleys. So our engineers spend a whole lot of time looking at charts like this and at the harness conception. The ones that we look at are a little more complex, but it's power versus time. And so what this represents is a vertical takeoff and landing aircraft where you get that big spike in power at the beginning because it's taking off vertically, you get a whole lot of power. Takes off, transitions to horizontal flight, and it's got a wing. So all of a sudden your power requirement drops way down. And then you come in for a landing, and it all of a sudden hovering again, goes way back up. You come down towards the ground, and then let's say you need to do a go around. So you gotta go back up, through somewhere else, and then come back down at a high power level and you're hovering. So when you're above the blue line, you're above the average power. When you're below the blue line, you're below the average power requirements. And with a hybrid system, one of the things you can do is engines, whether it's a piston engine or a turbine engine, they really like to run at a steady state power. You can design an engine around one power level, one RPM. You can make it really efficient. That's one of the things that we can do that you can't do in a conventional aircraft. So you design the engines and the generator section of the hybrid around that average power. And when you're above that line, you're pulling power out of the batteries. When you're below that line, you're pushing power back into the batteries so that your engines basically just run around the average the whole time. And so what that small engine and generator running at high power is a lot lighter, cheaper, and more efficient than a really big engine and generator that's running at a fraction of its required power. And this is something where we get a lot of efficiencies out of hybridization in many of these vertical takeoff aircraft or short takeoff and landing aircraft where they need a huge amount of energy for a short period of time, and then a huge amount of power, and then the power requirement drops away. So there's a term out there called range extender, and in hybrid electrics, I hear people say, well, we use a generator as a range extender. This is a term that I don't particularly like because it doesn't really play out that way when you actually get into the design process. So the concept of a range extender is it's a battery electric aircraft anyway. We're just going to put a little fuel tank and generator on board. Since that fuel is so much more energy dense, we're going to get much more range out of it. And that engine and generator is a range extender for the aircraft. So the problem with that is you can do that. Back to, you can put a turbo fan on a Cessna 172, doesn't mean it's a good idea. You can do this. But once you've gone through the process of I'm putting a generator on the aircraft, now you're going to put a fuel tank on the aircraft. Well, I'm an engineer by background. We like to optimize things. And so then you say, okay, I've got a battery on board, I've got a fuel tank, I've got a generator on board. Let's start optimizing this. Well, wait a minute. The fuel's got 20 times the energy density of the battery. So let's take a little bit more of the battery out, let's put a little bit more fuel in, and maybe let's give some of that battery weight back to payload, and now I've got a better aircraft. That worked pretty well, so let's do a little more of that, let's do a little more of that, and then all of a sudden you have no battery in the aircraft anymore, and you've optimized it, and you've actually got a more efficient aircraft than the one that had a huge battery pack on board, and you can do more with it because it's got more payload. So the challenge there is, once you put a fuel tank and a generator on board, you can start optimizing it, the role of the battery changes. Batteries aren't currently great for storing energy in our context, in aerospace. They will be 20 years from now, but we're not there yet. But one thing batteries are really good at is instantaneous power. If you want that energy out of the battery, and you want it all right now, you can get it right now. Whereas if you've got a fuel tank, you're limited by how fast that fuel can move through your engine to turn into power. And the engine's got a certain size. Your battery pack, you can ask for more, and there is a limit that's driven by heat chemistry, but that limit is way up there. So batteries are really good at delivering power, and even a small battery can deliver large amounts of power for a short period of time. So once you hybridize an aircraft, you don't really have a range extender. The generator and the fuel tank, those are your primary source of energy. What you have is a battery that's a power booster, and you can look for interesting ways to use that battery to boost your power, whether it's taking off as a vertical takeoff aircraft, whether that is a short takeoff and landing aircraft, you get off the ground at 100 feet, lots of things you can do with it. So, thinking about what the battery does versus what the fuel does in a hybrid electric aircraft, the fuel is really your energy. That's where all your endurance comes from. The battery, there is energy in there, but it's all the surrounding area. It's all of the fuel. The batteries, though, are where you get these temporary power spikes. And if you want to do things with that aircraft, where occasionally you want a whole lot of power, all of a sudden you've got a lot better ability to do that than you've ever had with conventional engine. So what does it mean when we see prototypes of battery electric aircraft flying? I mean, I actually demoed 2 aircraft here at Oshkosh like 8 years ago. I mean, there are a lot of battery electric prototypes out there. Some of those are scaling up nicely. Those are bitches with battery electric doors. There are a lot of things though that we're seeing, and they look really impressive. So what I'm about to show you here, I'm putting a bunch of disclaimers up here, is a reference VTOL aircraft that we modeled at Vertigo. We've got some of our own designs. We don't actually develop our own aircraft. We've got a lot of design tools that we use, and so we need to have some of our own designs that we can mess with that are usual designs that aren't our customers' aircraft. So we took one of our VTOL aircraft and we said, okay, let's model this thing either hybrid electric or battery electric. and see what really happens and what's possible. So this represents one specific aircraft that we did, but your actual mileage may vary. You know, any different aircraft we look at can get slightly different results, but the same thing is generally going to be true, the same trends. So we took this particular VTOL aircraft and we said, all right, how much battery can we put on board? So there's a thing called the weight fractions of the aircraft. Basically, how much of the overall maximum takeoff weight of the aircraft is dedicated to different systems. About the best you can do with batteries is 40% of the max takeoff weight of the aircraft, and that's a lot. So if you think about it, you've got aircraft sitting there, the airframe, the passengers, the motors, engines, landing gear, avionics, you name it. All of that stuff is 60% of the weight, and then 40% of the weight is just your battery packs of the aircraft. That's a lot. But there are certain aircraft where that's feasible. So we use that, that's that dotted line goes across there. And then what we said is, all right, as we want to go farther and farther, how far can this reference aircraft design go before we have to cross that 40% line and the battery pack's just too big to fit in the aircraft? In this case, we got 80 nautical miles. So we said, okay, that's interesting. I mean, that's not real far, but this is a VTOL aircraft. There are a whole lot of these missions people are talking about. Let's hop across the city. That's a lot shorter than 80 miles, 130 kilometers. So, all right, that looks kind of compelling. But we got a problem because we actually can't access 100% of the energy in that battery pack. And so when you charge or discharge a battery, there's a thing called SOC, state of charge. And that's basically what percent is the battery full. You know, are you 100%, 0%, somewhere in between. There's a problem with getting a battery all the way up to too full because you tend to really wear the battery out. If you try to fill all the way to 100%, the battery's not going to last very long. You can do it, but you're not going to get very much lifetime out of it, and that's an economic problem. On the other hand, if you go below a certain state of charge, the electrons are in there, but you can't have them the way you want them because the rate that you're pulling them out impacts whether they're available to you. There's a thing called voltage setting, which says you get the low state of charge, you may have a bunch of energy left in the battery pack. But if I try to pull a lot of current up, pull a bunch of power out of that battery right now, the voltage settings, the voltage drops, and you get into this death spiral where because the voltage drops, I need to now pull more current, and I'm pulling more current so the voltage drops even farther. And I can tell you as someone who flew some of the very early battery electric aircraft, I had to do a go-around once on battery electric aircraft that was in relatively low state of charge. It's not very confidence-inspiring when you push the throttle forward, and initially the propeller spins up, and then it bogs down and actually slows down because you pushed the throttle forward. And so getting that bottom part of the state of charge out of the battery pack is a real challenge. So all that is to say, we apply that, can't get all the power, so we went from 80 nautical miles down to 50. 50 is still okay, we can use that. Okay, but then batteries lose capacity as they age. You know, this phone is not as good as it was a year ago. Likewise, in an aircraft, that battery, it has to deliver its power on the last day it's in service, not just the first day it's in service. So you've got to derate the battery pack. Typically, that's about a 20% derating factor. So all of a sudden, we've gone from 50 nautical miles to now 40 nautical miles on this aircraft. Okay, that's still 40 miles. Maybe I can go somewhere. All right, how many people here have ever flown into a headwind before flying an airplane? A to point B. You've got to actually have enough energy on board to fly from point A to point B, do a go-around, that takes a lot of power, and then go somewhere else, and then land the aircraft. All of a sudden, we don't ever intersect with that red line anymore. The aircraft needs like a minimum of 55% of its weight dedicated batteries just to do a 0-minute flight legally. So basically, in order to leave the ground and land back on the ground, 55% of that weight has to be batteries. And so the challenge with battery electric aircraft, it isn't about that curve. It's about layering on all of the realities of batteries and the realities of actually doing real-world flights. And so you absolutely can do test flights in an empty aircraft with no payload on board, under test flight parameters, with no reserves, all these things. You can go a long distance. When you factor all these things in, you get back to the Cessna 172 with 4.6 gallons on board. And that's a real challenge. So now let's look at the same thing for hybrid electric. So we put a hybrid electric system in there, and that green line that never actually crosses the 40% threshold says, we just keep adding in more fuel. You know, there's, at 0 miles, there's a certain weight to that hybrid system because the engine, the generator, the power electronics, all of those things have the same weight whether you've got 1 drop of fuel on board or 100 gallons of fuel on board. So right off the bat at 0, we've got about 30% of the aircraft dedicated to powertrain. But then as we add fuel into the upper range, that fuel is so energy dense that we get all the way up to 400 nautical miles in this same aircraft design, and we still haven't crossed over that magical 40% threshold where it's too heavy to be usable. And even when we put in the reserve energy, I think this is VFR reserves, go around 30 minutes, land somewhere else, that just bumps us up to that other curve, the green curve that's just above the gray curve. It doesn't move the curves hardly at all, because that extra fuel is so energy dense, we really didn't have to put that much on board in order to get that extra endurance. So these are all reference numbers. A motor glider will look a lot better than this. A really heavy VTOL aircraft or a really fast aircraft is going to look worse than this. But every aircraft out there, whether it's going to be battery electric or hybrid electric, we've got to factor all these things in. And it's really important to understand, are we actually going to be in a reasonable scenario, or do we have an aircraft that looks really cool in test flights, but it's fundamentally a dead end because we can never get enough battery on board, at least not in the near future. Maybe 20 years from now, maybe 15 years from now, but not the things we can put our hands on right now. So, looking at this another way, you've got your battery available energy, you've got 100% of your energy in that battery pack, but you got to kind of chop 10% off the top and 20% off the bottom if you really want that battery to be usable and last. So now we're down to 70% of that left. And then, since it ages, because batteries behave like the things in this phone, we got to chop another 20% off as you wait. And so what you kind of wind up with there is if you thought you had a 100 kilowatt hour battery pack, you only really have 56% of that left that's usable. You have a 56 kilowatt hour battery pack that weighs as much as a 100 kilowatt hour battery pack. You got to carry the whole thing off along with you. So what it means when we see all these prototypes flying is some of those are actually going to work. They're high liberty aircraft, they're really efficient, and all the numbers close. Some of them aren't going to work. And flying a brand new prototype with a brand new battery under flight test conditions with no payload and with no headwinds, no ATC reroutings, and all those things, that's very different from certifying an aircraft and selling it and putting it into service. So how does the performance of a hybrid aircraft differ from the battery electric aircraft? Well, we talked about range, and range is the obvious one. You know, this is a similar design case where we're looking at range centered on Oshkosh here. You can see that very inner circle for current batteries, one that's out a little bit, 2 times improvement in battery energy density, that's just a little more. That outer circle is what we can get with the hardware we're running right now in Florida at our R&D center. So, big difference in range. compare gas or jet fuel to electricity, buying electricity off the grid is a lot cheaper per kilowatt hour than buying jet fuel or gas. But you've now got this battery pack that's got a TPO that's in the airplane. I'll give you an interesting number to think about here. Tesla Model 3 battery pack. The replacement battery pack for that car is $16,000. Is an aircraft battery going to cost more or less than an automotive battery? The guesses. More. How much more? A lot of times more. So take that $16,000 and multiply it by 3, multiply it by 5, you pick your number. It's a really expensive component inside that aircraft, and it's got a finite TPO in that aircraft. So the hourly battery reserve is one of the most important things in any electric aircraft, whether it's a hybrid aircraft, because all of our hybrids have battery on board, or a fully battery electric aircraft. The difference being hybrid aircraft, you're typically talking about batteries that are about a tenth of the size of the ones that we typically work with on a fully battery electric aircraft. So there's a 10x difference there in the cost contribution. One thing to really think about when designing electric aircraft is it's easy, relatively speaking, to design an aircraft that can be either battery electric or hybrid electric if you do that from day one. If you design solely around batteries and then realize later on you want to upgrade it to hybrids, that can be very, very difficult because engines and generators don't like to be switched. They kind of are what they are. They have a certain shape and a certain size. Battery packs, on the other hand, are typically made of thousands of small battery cells. So if you want to make some weird shape of battery pack, you can actually do that. And so as you're thinking about designing an electric aircraft, design it so that you can fit the hybrid components in. Because if you've got the right volumes and CG positions for the hybrid components, then as batteries get better, and eventually they will cross the threshold where you're going to want to consider, do we swap these out? You can design a battery pack to fit in the footprint that a hybrid generator is in, if you can't always do the reverse. So rationales for hybridization, it's the range, it's the mission planning, it's the safety margin, it's getting high utilization, it's getting out and back with the infrastructure, it's being able to certify the aircraft, and it's dealing with the fact that battery aviation in 2021 is like cars in 1995. So we're in the mid-90s right now. Look to the mid-90s automotive industry for what's going to happen next over the next 10 years. That's going to be a pretty good indicator. So we've gone through how performance differs, and it's not just range. There are a lot of things. And so just to go through some conclusions and an overview, why do we electrify? It's really primarily to build aircraft you can't otherwise build. It's not to do the equivalent of the turbofan powered 172 or the original XP-59 jet. It's to get to the point where we're really designing airplanes around these new capabilities, typically with the purpose of reducing emissions, lowering noise, and lowering cost. So what is a hybrid aircraft? It's basically a bridge between conventional power and battery electric, and we've got a lot of the elements of conventional power, whether it's liquid fuel in an engine, or batteries, whether it's the battery pack and the electric motors. Electric aircraft versus electric cars, it's 1995. That's probably enough said on that, and you can look at all the analogies that brings in. Hybrid power plant is really something that's got an engine, generator, power electronics, cooling systems, battery pack, and control systems, and while that's a rendering on one side, the other one there, we've got systems that are running. In fact, we've got two of those running together out on the ramp today for some testing in Florida. We're putting a lot of time on these systems and we're shipping out the board to customers who are using them for test aircraft. So a lot of benefits of hybridization. One that we didn't talk a lot about, though, is infrastructure. In addition to range, high utilization, out and back missions, we've got all the infrastructure we need. We don't need a charging station. All you need is refueling for a hybrid electric aircraft. And So that concludes the presentation, and I'd like to take any questions that are out there now. Thank you very much. All right, I'm going to start going around here, so I'll start with you, sir.
Hi, what about hybrid aircraft using hydrogen fuel cells?
Okay, the question was, where do hydrogen fuel cells come into hybridization? And the answer there is there are actually a lot of parallels in a fuel cell aircraft versus hyperelectric aircraft. We've even done some research for some customers in that area. There are challenges with hydrogen fuel cells, and that has to do primarily with storing the hydrogen and making that weight effective and space effective, and then also the weight of the fuel cell itself. But a fuel cell powered electric aircraft often looks conceptually a lot like a hybrid electric. You pull the generator and engine out, you put the fuel cell in, you still need the battery pack as a buffer between the other systems, and you still got a lot of the same control systems. So I think we're going to see some activity in hydrogen, particularly in Europe where there's a lot going into infrastructure. It's a difficult market though, because hydrogen is kind of trapped between hybrids, which are compatible with all the infrastructure we have now, and batteries, which are coming in about 20 years, which will obsolete the hydrogen systems. And so you got to pay off all the investment in the infrastructure and developing the systems in a finite period of time before they go obsolete. So hydrogen is interesting, but I'm a bit skeptical. But it's a good question. Question here.
How much does your 150 kilowatt power pack weigh?
So that 150 kilowatt power pack is heavy because it's got a bunch of non-standard things on it. That's about 1,200 pounds, which is way too heavy to go into production. That's why that's a development system only. That's going into aircraft that have more payload basically than they need to get the airframe in the air right now. That production system that you saw is 185 kilowatts and it's about 600 pounds. So that's got a much better power weight ratio, and we're then working with some things for the long term to go from there. Good question. Okay, over here.
What about solar?
Solar? So the big Achilles heel with solar isn't something you can solve with technology. The problem is the sun. So there is a finite amount of watts per square meter that fall on a given area. And this is something I'm just now, I know that with hybrids, this is going back to my days with battery electric aircraft. We used to get asked a lot, why don't you put solar panels on the wing? The answer to that is aircraft aren't big enough to ever have a meaningful amount of contribution from solar power. And it's not about maybe someday solar panels will be more efficient. You can go all the way to assuming the solar panel is 100% efficient and you're only ever flying on cloudless days at noon at the equator, which is the absolute best possible scenario for solar. There's still not enough energy coming from the sun, and the sun is the Achilles heel. If you want to do solar for aviation, put the solar panels on the roof of your hangar. Charge the aircraft when it's on the ground and fly it, and don't worry about putting that complexity on the aircraft. There are good ways to use solar energy to make flight possible. Putting solar cells on an aircraft, I mean, we all saw solar impulse. They went around the world. That's an incredibly impressive program. That's almost as good as you can ever get with solar power. You've got an aircraft with a span of a 747 that can barely lift one person. And that's because you need that much area to get enough energy from the sun to make the thing go. Yep.
Can we talk about the airlines for a second? So,
sure.
With what Airbus is doing, for example, can't we use the battery for the APU, and maybe you could drive the wheels during taxi in the first 30 miles an hour, because the plane is in descent half the trip. Maybe you could recharge a smaller battery, and then you don't have the clutch issue, you don't have any of that stuff. Is that feasible?
So some of that is feasible, and there are multiple companies that are working on ground taxi capabilities with electric motors in the landing gear, so you actually don't have to fire up the turbines until you're right at the threshold of the runway. That saves you some energy. Now, if part of that question, reading between the lines, I think part of that is we were asking, can you regen some power on the descent and use that? Unfortunately, that doesn't pay off. And back when I was at the program. We actually have software in our aircraft to do that. We messed around with it, but we knew it wasn't going to pay off. We went ahead and measured it anyway. The problem there is, in a hybrid car, you're recovering your braking energy. We've been doing that since the Wright brothers with airplanes, because when you're flying somewhere, you pull the power back way out from the airport, and you get on a parabolic trajectory where you're starting to use the kinetic energy and the potential energy of your height, so that you actually pull the power back way before you get to the airport, and you're kind of going on momentum and you're burning that up. If you then try to regen with reversing the flow and you're basically driving the propeller as a generator to power back the battery, you have to then fly at full power to get closer to your destination, because once you do that, you're putting extra drag on the airplane and you're going to descend steeper, and unfortunately, it never pays off. You always wind up on the back side of that curve. So it's a good question. Unfortunately, it doesn't pay off. Yes?
So a lot of kind of what you talked about is smaller systems with colorful aircraft, but in terms of larger like transportation aircraft and big turbofan 737s and commercial aircraft, is there really any place for electric at this point?
So the question was basically, how does electrification play out in big transport category aircraft, things like Boeings and Airbuses? It's really, really hard. In the near future, there's a lot that we can do with smaller aircraft. Let's say 19 seats and lower. It gets even more exciting. 9 seats and lower. When we're talking about 2, 4, 6, 8 seats, there are a lot of things we can do. The problem with those bigger aircraft, it isn't actually the size of the aircraft, because you can scale things up and just make it bigger. You put a bigger engine on board, a bigger generator on board, all that works. The problem is that Boeings and Airbuses also go faster. And with more speed, it actually goes up as the square of the speed, where you need a whole lot more power. And so when you go bigger, you also wind up wanting to go faster. And it's the faster part of that where it falls apart. So if you wanted to build a transport category 400-seat aircraft that cruised at 120 knots, you could probably do it. And the numbers are probably close. The problem is no one wants to sit on that aircraft for long enough. And so when you get up in that range, you want to go 550 knots. And that just gets us even farther from where batteries and even hybrids are right now. So good question. Yep.
You mentioned distributed propulsion. NASA's been speaking about that for quite a long time as well. It seems as though, for example, insects are very efficient flyers and very controlled flyers. Has there been much study in using the electrification of aircraft to, say, better mimic the flight patterns and methods and control systems that an insect is using to attain what they're able to achieve?
Yeah, I think you do see some of that. It's not necessarily literally doing that, but the example that I would encourage you to go see, if you can walk literally right over there in about 5 minutes, is Blackfly Opener. They've got an ultralight VTOL aircraft that's got, remembering right, 16 propulsion units on it. So they've got it merged together, the attitude control, the propulsion, and all that. And they kind of are doing that. So we are seeing people use the power in very different ways. And that is one of the exciting things about electrification, whether it's batteries or hybrids. Once you can flow the electrons all over the aircraft, you do all kinds of interesting things with it that you couldn't do before when it was really only efficient to have 1 or 2 power plants on it. Yep.
The Reynolds number's way off. For an insect to scale, the Reynolds number.
The Reynolds number is not here for scale, yes. You're talking about insects with airplanes. Yeah, good point. Yep.
Eric, what do you see coming up in improvement in power density in battery technology?
So in battery technology, Moore's law for batteries, this is what actually happens, is they get better at about 5% a year for energy density. So over a couple decades, that leads to a whole lot of improvement if you compound that every year. In the next 5 years, it's not going to be that much different than it is now. And I'll give you something to think about. we have to use certified, demonstrated safe technologies to go into an aircraft, because we're all focused on safety. If someone came to us right now today with a new battery that was 30% better or 50% better or whatever, that has to go from being a lab experiment to being a full-size battery, to being a battery pack, to having a supply chain, to having statistical data, and then to going through a certification process. We're going to see this coming a long way off. There are going to be applications in other industries that can take more risks and move faster than we can. And so we're going to see these battery technologies coming. But if you can't put your hands on it right now, it's not useful in the next 5 years.
Another question.
Yep.
Can you talk about Gabriel Duval's zero motorcycle engine motor glider?
So I know of it, but I don't really know much about it. So one thing I will say is, you saw some of the pictures of aircraft I worked on previously. High L over D aircraft, so you use the word motor glide. The higher the L over D, the more efficient the aerodynamics of the plane are, and therefore the less energy you need on board. And so I will say that one of the niche markets right now that looks really, really good for batteries, and they're already there, are self-launching sailplanes. I'm a glider pilot myself. If you want a self-launching sailplane, go buy one that has a battery electric system. Because all you need to do, again, you need power for a short period of time. You don't need lots of energy. You basically need to replace a couple 3,000-foot toes and then you're up and you can fly around your thermal, ridge soar, whatever. So high L over D aircraft, like motor gliders, are actually a really good place to work with batteries alone, and you may not need hybridization. Okay? Yep.
Do you have any plans for a plug-in hybrid?
Question was, we have plans for a plug-in hybrid. Not specifically, although our systems could be implemented that way. That's really our customer's decision. You could take any one of the hybrid systems we're working with any of our customers and plug the battery section of it into a charging station if you wanted to. In practice, because the fuel represents so much of the energy that's on board the aircraft, you don't get a huge benefit from doing that in aerospace, and a lot of our customers, they want to actually charge the battery in the cruising phase of flight, so that when you're on the ground, the airplane's basically ready to go. You don't need to wait, you don't need to charge things on the ground, the plane's ready to go when it hits the ground. That tends to be the preferable operating environment, but it's absolutely